Alright guys, welcome to my wonderful home office, aka storage room, aka Grant's playroom, aka whatever else you want to call it. So what we've got here is I'm going to try to real quick work out a couple of problems for you from the homework assignment because I know that you probably tried them, or at least I'm hoping you tried them, and I'm not sure you did so well. So I'm going to try to work out a few of those for you. However, before I get going, I wanted to let you know that several of the problems I decided to omit. And y'all are probably familiar with me doing this. So if you checked the Twitter last night, aka right while I'm recording this, not while you're watching it, but I just tweeted a picture that showed the problems that you could omit. Now I'm going to put that same piece of paper on the camera here in just a moment. And if you need the sub to pause the video so you can write down which ones to omit, go ahead and do that. But here it comes. Now this is going to be kind of crazy because I'm going to have to hold the webcam with one hand and try to write and work problems with the other. So we'll see how coordinated I can be. In the midst of this, Miss Keller is trying to text me to ask about questions about some video conversion. So let me pause and answer her text message right quick. Alright, so here we go. And I know Michaela is laughing at me right now because that I'm helping Miss Keller at 9:36 p.m. which I'm sure most of y'all are already in the bed by 9:36 p.m. because I know that's where I would rather be. So I'm going to turn on this light here so you can see the pages that I'm about to show you and see if I can be multi-talented here. Alright, okay. So here are the questions that you can omit. They are on the first page, questions 4, 8, 9, and 10. On the second page, there are no questions that you can omit. On page 3, you can omit questions 5, 6, 7, and 10. On page 4, questions 2, 3, and 6. And then on page 5, questions 3 and 6. Alright. And I'm guessing this isn't going to work because my arm's going to put a shadow over it. So maybe we can do this. Let's see, how could I do this to where I'm not going to get a shadow? I guess I'll just have to do it like this. Alright, so we're going to look on the first page. And what I've done here is I've gone through and selected what I felt to be the most difficult problem. And I'm going to work one from each page for you. So on the first page of the homework assignment, I felt that problem number 2 was the most difficult. So let's see if I can work out problem number 2 here for you. And this is working gloriously. Alright, problem number 2 says, in 1985 in San Antonio, Texas, an entire hotel building was moved several blocks on 36 dollies. The mass of the building was about 1.45 times 10 to the 6 kilograms. So that's the first thing I'm going to write. I'm going to write down the mass is equal to 1.45 times 10 to the 6th kilograms. So that's our first piece of information that we know. Mass of the building, 1.45 times 10 to the 6 kilograms. If 1.0 times 10 to the second megajoules, so this is going to be work, 1.00 times 10 to the second megajoules of work was done to overcome the force of resistance that was just 2% of the building's weight. So here we go. Force is 2% of the building's weight. (2% of the building's weight. So that's what our force is. How far was the building moved? So how far, we need to know a distance of some sort. Now, on this first page, all of this first page is about work. And the formula for work. Work is equal to force times distance. Work is equal to force times distance. So everything you're going to be looking at here is going to be talking about a force, a distance, or work. So now we know the mass, we know the weight, and we know the force. Now if you think back to Newton's second law, remember Newton's second law let us know that force is equal to mass times acceleration. Mass times acceleration. So keep that in mind as we go through this. Now also on the mass. For these problems, mass has to be in kilograms. So we're all right here with the mass. But the work needs to be in joules. This work right now is in megajoules. So we need to convert that megajoules. So the prefix mega, M, is equal to 10 to the 6th, or 1 million. So we have to convert that 1.0 times 10 to the second megajoules into actual joules. So here's how we're going to do that. So we take our 1.0 times 10 to the second megajoules, put that over 1, and then we bring in the conversion. And I'm trying to write and watch the computer screen to try to keep it all in check here, and we'll see how well this works. Alright, so a joule, or there is 10 to the 6th, or 1 million joules in 1 megajoule. So remember, when you're working out these conversions, you got to have a top cancel with a top and a bottom cancel with a bottom. So a megajoule there cancels with a megajoule there, leaving us with just joules, which is what we're looking for. And again, in these problems, you have to have the certain units, and that unit that we're looking for here is joules. So when we multiply that out, our number of joules becomes 1.0 times 10 to the 8th joules. So that is our work. So we can go up here and change this work right here to 1.0 times 10 to the 8th joules. 1.0 times 10 to the 8th joules. Alright, so now we can also calculate the force, because it says right there the force is 2% of the building's weight. So force, where you go? Force is going to be equal to 2%, so 0.02. That is the decimal form of 2%, times the building's weight, the building's mass, which is 1.45 times 10 to the 6th kilograms. So when you multiply those two, 0.2% times 1.45 times 10 to the 6th kilograms, you get a force of 29,000. And what's the unit of force? The unit of force is the Newton. So you get 29,000 newtons as your force. 20,000 newtons as your force. Alright, so again, let's think back. What are we trying to find? Well, we're trying to find the distance there. Trying to find distance. So work is equal to force times distance. Force is mass times acceleration. To find distance, we need a force and a work. Well, we just calculated a force right there, and we have our work up here in the megajoules. So now we're ready to plug into our formula. So again, work is equal to force times distance. Our work, which we calculated into joules up here, 1.0 times 10 to the 8th. 1.0 times 10 to the 8th is equal to our force, which we calculated right here above it, at 29,000 newtons. So 29,000 is multiplied by our distance, which is what we're looking for. So the opposite of multiplication is, of course, division. So we move this over until we get 1.0 times 10 to the 8th divided by 29,000 is equal to D. So when you plug that into your calculator, your distance is 3,448 meters. 3,448 meters. Now, of course, as we're going through this, if you need to get the sub to rewind, fast forward, pause, replay, whatever, ask he or she to do that. That way you know what's going on. So that, like I said, I believe was the hardest question on page number 1. So now we're going to move to page number 2. And again, what I believe to be the hardest question on page number 2. Now, page number 2 is dealing with, let me double check. I believe it to be kinetic energy. But let me double check something right quick here for you. Pause for refreshment here. You can see I'm thoroughly organized in this process here. Yes, page 2 deals with kinetic energy. So I'm going to flip this page over, and we're going to go to page 2. Now on page 2, I'm going to work out here for you problem number 7. So problem number 7 on page 2. So on page 2, problem number 7 reads, the brightest, so right here, number 7, the brightest, hottest, and most massive stars are the brilliant blue stars designated as a spectral class O. If a class O star with a mass of 3.38 times 10 to the 31 kilograms has a kinetic energy of 1.0 times 10 to the 42nd joules, what is its speed? Now, I'd marked out that line, express your answer in kilometers per second, a typical unit for describing the speed of stars, because originally I didn't think I wanted you to do that, but then I decided that I want you to do it, so I'll show you how to do that as well. All right, so reading the problem, a couple pieces of information that we can pull out of this problem that are pretty important and pretty essential. Now, the first piece of information that we can pull out is the mass. The mass of the star, I believe it was. Isn't that what we're talking about? Yeah, the mass of the star was 3.38 times 10 to the 31 kilograms, which you can't see. So there we go. 3.38 times 10 to the 31 kilograms. And that is the mass. And again, you need it in kilograms. Mass you always want in either grams or kilograms. In the cases of these equations, we're going to go for kilograms. All right. And then your kinetic energy. It gives you the kinetic energy value equal to 1.10 times 10 to the 42nd joules. And the problem is asking you to find the velocity. Now, if you remember the formula for kinetic energy is equal to 1/2 mass times velocity squared. The formula for kinetic energy, 1/2 mass times velocity squared. And feel free to yell at the smartboard anytime that you want to, because I know this is probably not very fun. All right, so 1/2 mass times velocity squared. We have a mass and we have a kinetic energy, so we're going to find a velocity. So this is a pretty simple algebraic problem. So let's start plugging in. Kinetic energy 1.10 times 10 to the 42nd is equal to 1/2 our mass
3.38 times 10 to the 31 kilograms, we'll just leave that kilograms out, times velocity squared. So now we need to multiply these together. So we can just bring this guy on down. 1/2 times 3.38 times 10 blah blah blah. So you get 1.69 times 10 to the 31st is equal to velocity squared. So right now these two guys are multiplied. Opposite of multiplication is division. So you're going to divide these two. And that's going to give you v squared. 1.10 times 10 to the 42nd divided by 1.69 times 10 to the 31st. Again, as I'm going through this, if you need the sub to pause, rewind, ask him or her to do that. And they should be able to do that fairly simply. All right. And then, so now we need to divide this out. And when we divide that out, we get 6.51 times 10 to the 10th is equal to velocity squared. This is squared, so to unsquare it, we square root the other number. That will give us velocity. And velocity becomes a big number of 255,124.99. Now this guy right here is in meters per second. Meters per second. Remember, it asks you to put the answer in kilometers per second. So let's see if we can do that. We got 255,124.99 meters per second. So all we're concerned about is the top part. We don't need to mess with the bottom part on the conversion whatsoever. So we want kilometers. Meters is on top there, so it has to be on bottom over here. So that means kilometer is on top, and there are 1,000 meters in 1 kilometer. So now top times top, bottom times bottom. So what we end up doing is dividing this number by 1,000. And when we do that, we get 255.12 kilometers per second. So there should be the answer to number 7 on page 2. Now on page 3, remember on page 3, that was the one that you got a lot of omit problems from. So you only ended up doing 2 problems on page 3. So let's see, I'll do number 10 for you. So number 10 on page 3. Now you probably got like a B or something on this that didn't run off because I only ran off the first page. So we're just going to do part A. It's going to be a part A. That's kind of a joke. Kind of like a party, but part A. Okay, maybe not too good of a joke. All right, so let's look at number 10 on page number 3. Number 10 on page 3 reads, when April Moon set a record for flight shooting in 1981, the arrow traveled a distance of 9.50 times 10 to the second meters. Suppose the arrow had a mass of 65 grams, and at the angle at which the arrow was launched was 45 degrees above the horizontal. Question A. What was the kinetic energy of the arrow at the instant it left the bowstring? Hint, review section 3E to determine the initial speed of the arrow. Now, if you think back to a class when we talked about this section is about potential energy, GPE. And that's why you had so many of them that you could omit, because if you remember back to class, there was 4 or 5 different bullets about potential energy. But again, I only wanted you to be concerned with the GPE, the gravitational potential energy, and there were only 2 problems that were associated with that. So that's why you had so many you could omit. Now, remember, in a closed system, GPE and KE can be equal. So that's the assumption we're going to be working on here in problem number 10. Now, let's read through problem number 10. The arrow traveled a distance, so a distance of 9.50 times 10 to the second meters, had a mass of 65 grams. 65 grams. Now again, and then it says the initial velocity. Velocity initial. Velocity initial is the tricky part here, because velocity initial is always 0. meters per second. Now, at this point, some of you smart fellers are going to already know the answer because you can see where we're going here. Because remember, GP and KE are equal, but again, that's our formula for that is mass times gravity times height. Mass times gravity times height. Or, the more way that we're going to use it here, mass times acceleration times height. Because again, gravity is an acceleration, acceleration is gravity, so we can interchange those. Or we could use the kinetic energy formula of 1/2 mass times velocity squared. Which one of these two formulas match up best with the information we have? Probably this one right here. So let's see what we can get here. Kinetic energy, because again, that's what you're trying to find in this problem, is it's wanting you to find the kinetic energy. So kinetic energy equals 1/2 of our mass. Our mass is 65 grams, but remember I said we need it to be in kilograms. So 65 grams over 1, grams on top there, gram has to go on bottom right there. That means kilograms are on the top. 1 kilogram is 1,000 grams. So I'm going to slide over here. So what we end up with is 65 divided by 1,000. So that gives us 0.065 kilograms. So that can come up here. And then our velocity, which was 0, but that's squared. So 0 times 0 is 0, 0 times that is that. And so kinetic energy is 0 joules. Why? Because anything multiplied by 0 is 0. And that's why I said some of the smart people probably noticed that over here when you realize you were going to use this formula. So that's page, I think, 3 now. Now we're going to go to page 4. Page 4. And let's see, what did I think was the hardest problem on page 4? I think question 5 is the hardest problem on page 4. So let's look at question 5. Flip this over to the next page so I got plenty of room to write on. And let's look at question 5 on page 4. Question 5 on page 4 reads, suppose a motorcyclist rides a certain high-speed motorcycle. He reaches top speed and then coasts up a hill. The maximum height reached by the motorcyclist is 250 meters. If 255 times 10 to the 5th joules of kinetic energy is dissipated by friction, what was the initial speed of the motorcycle? The combined mass of the motorcycle and the motorcyclist is 255 kilograms, excuse me. All right. So a couple things here. Let's pull out what we know in this problem. So we first off that we know that the height that the motorcyclist was traveling was 250.0 meters. 250.0 meters. Then we know the kinetic energy that was dissipated to friction. So I'm going to put a little F down there to let us know that that was talking about friction. So the kinetic energy for friction was 2.55 times 10 to the 5th joules. 2.55 times 10 to the 5th joules. We don't know our velocity. That's what the problem is asking us to find. And then we know that the mass of the rider and the motorcycle, oops, sorry about that, let's move down. The mass of the rider and the motorcycle is 250 kilograms. So, and the formula that we have for, or that will give us velocity, that has an open part velocity, is the kinetic energy formula. Kinetic energy equals 1/2 mass times velocity squared. Now, you also have to remember that in a closed system, that the gravitational potential energy and the kinetic energy are equal to one another. And And that's something you always got to keep in mind. So, and remember that the formula for this one is mass times gravity times height. We don't have enough information to calculate the kinetic energy. The kinetic energy we have is the kinetic energy due to friction. We don't want that. We want just the full-blown kinetic energy by itself. So to do that, we're going to have to use the GPE formula here. So our mass of 250 grams times gravity at 9.81. Remember, that is a constant number. It stays the same, does not change. And then our height of 250 meters. And when we do that, we get a GPE, a gravitational potential energy, of 613,125 joules. 613,125 joules. 613,125 joules. So that is our KE. So now we can go into our KE equals 1/2 mass times velocity squared formula. So KE is right over here, 613,125 is equal to 1/2 our mass, the 250 kilograms, times our velocity squared, which is what we're looking for. So now we multiply the 1/2 times the 250, and we get 125. Okay. Now since the 125 and the velocity are multiplied at this point, we'll need to divide them. So 613,125 divided by 125 is equal to velocity squared. When we divide these two guys, we get 4,905 is equal to velocity squared. If we square root the 4,905, that gives us just the velocity. So when we square root that, and this little shadow right here is from the camera because I got that light overhead. So then we get a velocity of 70.04 meters per second. That's what happens when you square root it. There you go. So that's page 4. And now let's go to page number 5. Last problem I'm going to work for you here. Wow, I've already been talking for 27 minutes and 33 seconds. It's got a little nice little counter thing going over here. So let's see, which problem did I think was the hardest on page 5? And page 5 is about power. Power, remember, is work divided by time. And let's see here, which one did I think was the most difficult here? They were all fairly straightforward, fairly simple. So I'll tell you what, let's just do the first one. Number 1. I think number 1 looks like the most difficult here. So number 1. The most powerful icebreaker in the world was built in the former Soviet Union. The ship is almost 150 meters long. So let's see here. We have a distance of 150 meters. And its nuclear engine generated 56 megawatts of power. So power is 56 megawatts. How much work can be done in the engine in 1 hour? So work is equal to what we're looking for, and time is equal to 1 hour. Now, just like on the kinetic energy problems and things, there's certain units that we need to have. Megawatts is not it. We just want standard watts. And then time, remember time in physics we always want in seconds. So the first thing we do is we're going to convert that megawatts into watts. So megawatts, 56 megawatts over 1. And remember from earlier that mega is a million. So a megawatts is up here, so it's got to be down here. So one of those is a million watts. So when you multiply that out, you get 56 million watts. 56 million watts. That is a huge number. All right. So let's do the hours now. So we got 1.0 hours. First thing you got to do is you got to convert to minutes. If hours on top's there, minute has to be on top there. There are 60 minutes in 1 hour. So now we got rid of the hours here. Now we got to get rid of the minutes. So if minutes is on top there, it has to be on bottom here. So that puts seconds up there. 60 seconds in 1 minute. So we get 1 times 60 is 60. 60 times 60 is 3,600 seconds. 3,600 seconds. So that is our adjusted time. And power. Or excuse me, yeah, power? Yes, adjusted time and power. So remember, power is equal to work divided by time. That is the formula that all of these questions on page 5 here will work off of. So we know our power is 56 million watts. We know our work is what we're looking for, and that's divided by our time that we calculated to be right here, 3,600 seconds. So right now they're divided. Opposite of division is multiplication, and that will give us W, our work. So when we multiply that out, the work that we get is another huge number, 2.016 times 10 to the 11th joules. 2.016 times 10 to the 11th joules. Alrighty. So let me return the camera back to the top of the monitor here so you can see my bright and shiny face and know that I'm still with you. So the rest of the class period, the rest of the time is yours to work on the remainder of these problems. I want you to work in small groups, no more than 3 people, and try to figure out these problems. They're not as difficult as I'm sure you make it out to be. Again, if you need to review the video, pause, rewind, what have you, do that. Before you leave today, I want you to at least finish page 1. And I want page 1 with your answers to page 1 on a separate sheet of paper in the box before you leave. So page 1 with your answers and work on a separate sheet of paper in the box before you go. All right, so that puts me at about 33 minutes here. That means you've got like an hour-ish to do like 1, 2, 3, 4, 5, 4 problems. An hour to do 4 problems. That's like 15 minutes a problem. You can do it. I will see you on Friday. Have a good one.